Howdy everyone, I'm Michael Pyrcz and I'm Associate Professor at the University of Texas at Austin, and I record all of my lectures, and this is part of my course, Introduction to Data Analytics and Geostatistics. And last lecture we talked about the issue around spatial bias, spatial sampling bias, and specifically how we have it almost every time we deal with sparsely sampled spatial data. Common for the subsurface, of course, where we're a bit focused. And so what we'll talk about in this lecture is one methodology to correct this problem known as declustering. So let's talk about the concept of clustered samples and how this occurs and how it impacts statistics. Let's make an estimate over an area or volume of interest in the subsurface. So it's a spatial problem. We got X and Y. This is in plan view, two-dimensional representation. It could be a three-dimensional body, doesn't matter. Now we have this area of interest. I drew an arbitrary boundary just like this, and I have my samples available to me. So I have 1 through 7 samples. Now I want to calculate the average porosity. Why would I want that average porosity? I want to calculate the oil in place over this area of interest, the entire area of interest. So the average porosity is part of an important predictive model for this volume or area of interest. All right, so let's take a look at these samples and ask ourselves a really important question. Are you comfortable using the average of the values at each one of these samples as the average porosity over this area of interest? Do you have any concerns? Do you think it would be fair? Do you think it would be potentially biased? Okay, let me give you a little bit more information and tell me if that would influence your decision. I'll tell you now that this part of the reservoir is systematically higher. It has a higher porosity, and this part is all lower porosity. Now, if we were to take those samples and just calculate the average, we got 1, 2, 3, 4 values there. And we have 3 values here. This is a smaller area. This is a larger area with only 3 values. Can you see how that would cause a bias? Now, let's go ahead and imagine what would happen if we were to continue drilling and the drilling looked like that. Now, are you even more concerned about using the average, the naive raw average from all of those data as the representative average of that area or volume of interest? I think I'd be concerned too. I'll tell you what, we love good news. We love drilling where things are really good over and over again because we'll get the best production rates, we'll get the highest mineral grades if we're worried about minerals. If we're producing water from aquifers, we'll drill where we get high production rates of water. We love good news. And so there's plenty of good reasons why we'd have more samples in this location here. We've already abandoned the idea of random sampling, and now we're just dealing with the data that we have available to us. Now, what would happen if we tried to use the well average, the naive average porosity, to represent the average over that area of interest? Well, this dotted line right here could represent the actual true porosity average over that entire area of interest. When we drilled the first couple wells, we were already somewhat more densely sampled in that high area, so we'd imagine we started out with a bias. We drilled a couple more wells in the lower area, and then as we continued to drill, we kept drilling more and more in that high area. And so as we had increasing number of wells, the well porosity average continued to go up, and this difference right here is a bias. We're overestimating the average porosity because we kept drilling in that high area. We were clustering the samples in the good locations. The naive statistic, the naive sample average, will become even more and more biased as we collect more and more data, clustered even more in the good or the high area. We need a method that corrects for clustered samples and gets us a more representative statistic. Okay, so let's talk about how to do that with a methodology we'll describe as declustering. Okay, so what we have in this example right here, let's give ourselves a data set to demonstrate this concept. And so what we have is we have an exhaustive data set with porosity at every location. Now, recall back from our basic statistics concepts discussions, the map of all porosity values at a sufficient resolution is considered to be, in fact, the population. So this map is the population. It's all possible porosity values. And so this right here, this distribution is the distribution of porosity over all of those locations. This should read porosity population. I called it realization because I used a geostatistical method to make the population, and we'll talk more about that later. Then what we actually have available to us are these samples. Now I hope everyone can see these samples here, regularly sampled, but then we're missing some samples. You notice that preferentially, we have sampled in a more dense manner in the highs, and in the low values, because of those missing samples, we have a sparser sampling. We're not quite having the same sampling density in the low values. So if you look at the sample distribution right here, what you can see is that it looks a little bit different. Now, you don't have to just trust me. Let's look at the summary statistic, the average. That's the thing that we're concerned about predicting. The true average, arithmetic average or mean, is 10% porosity. So if I calculate the average of this distribution, it's 10% porosity. The clustered sample, these samples that are shown right here at these locations in this distribution right here, is 10.48, 10.5%. The error is about 5% error in the average of the porosity. Now you might ask yourself, does an overestimation of 5% in the average of porosity actually matter? And what you'll find from many reservoirs around the world, overestimations of average porosity by 5%, resulting in an overestimation of oil in place by 5%, would probably be significant and could impact the way you plan, or even the decision to produce a reservoir or not, or to develop an asset or not. And so we don't want to have bias just because of the way we sample. And it can get worse and worse and worse. In some settings, I've seen it go up to as much as 15 or 20% overestimation because of clustered sampling. Okay, so what are we going to do about it? In the last lecture, I suggested we have two methodologies we can use to correct for bad sampling. And this methodology that we'll explain right now is known as declustering. Declustering is used specifically when the problem with sampling is clustered samples, which I just demonstrated, where you have sampled the good stuff, or you could have sampled the bad stuff, with greater density. So what we're going to do with the clustering techniques is we're going to assign to each datum a weight based on the closeness of surrounding data. In other words, if you're in a location, if that data is sampled in a location where there's not very much data around it, it's sparsely sampled in that location, it should get a high weight. It's more representative of more area or volume. If the data is in a location where it has a lot of data around it, it's very densely sampled around there, it's not providing very much new information, it should get less weight. It's not as representative of the volume or the area. Okay, and then what we can do is we can use these weights. We'll calculate a weight for every one of the data. We've got a column with all of the values of the data, and now we have a column with all of the weights of the data, weight for each one of the data. And we can calculate any summary statistic like the average with those weights included, a weighted average. And I'll show you how to do that shortly. You can even calculate the entire histogram, CDF, PDF histogram, using those weights too. So let's explain declustering. In the next lecture, we'll explain debiasing techniques. Okay, so the first methodology we have for declustering is cell declustering. This is a method for calculating the declustering weights by using a mesh of cells. So what we're going to do is we're going to go ahead and take our data set. Now, I hope you don't get confused. I did for this example here, I took from my book an example which had different data than what I've shown previously, but we'll go back to that original data. So don't try to map them out or figure it out. But this is just illustrative right now. So we take the data, the area of interest, this is X, this is Y. We put a mesh of cells on top. And now we have to calculate how much weight to put on each one of these spatial sample data. So what we'll do is if there's a cell and there's only one data inside the cell, that data gets full weight. It's going to get one weight. If we have a cell with 3 data, it gets 1/3 weight. A cell with 5 data, 1/5 weight, and so forth. Now you'll notice that we're doing 1 divided by the number of data within the cell as a amount of weight, and then we're scaling it by the total number of data divided by the total number of cells with data in them. Don't worry about that. It's not a big deal. This scaling just ensures that the summation of all the weights to all of the data is equal to the number of data. And that's a nice, consistent way to do this, because now what we have is we know the sum of the weights over all the data is going to be equal to number of data, and we know that when we have a datum with weight equal to 1, that's nominal weight. It means that that data is sampled perhaps in a location where we're not dense, we're not too sparse, we're not too dense. We're at the density of sampling we would expect if we had regular sampling. That would be weight of 1. And if we're going to be less than 1, it tells us we're taking data that's from a location where perhaps we have very dense sampling. And if we have a weight greater than 1, we're taking data from locations in which we have perhaps sparser sampling. All right, so that's the cell-based methodology that we're going to employ. Now, as I explained just now, what we would expect is that if the declustering weights are equal to 1 for that datum, that means nominal weight. Less than 1, reduced weight, because the data is densely sampled. It's too densely sampled in that spatial location. Greater than 1, it indicates that we have increased weight because we're sparsely sampled. Now let's go back to the original example that I showed previously. If we were to go ahead and take that data set that I showed you with some missing data and calculate the cell-based declustering weights, we'll find a weight of 1 is this, I don't know, kind of a pink color here. And these ones right here might be data locations with a weight of 1. Then what you'll see is a weight less than 1 are these blue colors right here, darker colors. And look, in the area where we have very dense sampling, we have weights less than 1. And then what we'll also notice is that when we have data in very sparsely sampled locations, like that's a perfect example, and that's a good example there, the weights are greater than 1. We can also take a look at the distribution or the histogram of the weights, and we can confirm that we range somewhere between about 0.5 to 1.5, and that'll vary depending on the problem that we're working with. But right here in the middle, about a weight of 1, these bars here represent nominal weight. Okay, now I should mention that some software programs that do declustering actually use a convention of the sum of the weights equal to 1. Not a big deal, it's just a different convention. In that case, the nominal weight is 1 divided by n. You can see that, so it's not too bad. Now let's look at what happens when we use our declustering weights. What we can do is we can update the distribution, the histogram, using declustering weights. Here's the original porosity samples. We would call this a naive histogram. We haven't accounted for spatial sampling bias with declustering. And we look at that and we have the true mean was porosity was 10%. The clustered sample mean was 10.48, error 4.8%. We saw this before. Now what we can do is we can go ahead and take the data values and the column with the weights. Now what's fascinating is that many of the methodologies for calculating statistics within software packages or plugins in Python actually allow you to include weights with the data. Why? Many people have been doing this, trying to find spatial weighting or other types of weighting on data to debias data. People who work in hydrology do it all of the time, and other types of spatially based scientific fields. So we can calculate any statistic weighted. In fact, if you think about this histogram right here, This histogram, if you look very carefully, it's frequency. Frequency of 1, that means we had one sample at about 6%. We had one sample at about 14.5% or so. We had 6 samples. Remember, so a histogram is just showing frequencies. And if you look very carefully, 1, 3, 5, 4, you see how they're all integer frequencies? They all reach these points right here, 1, 2, 3, 4, 5, 6, and so forth. And that makes sense. It's a simple frequency plot. Now look what happens when we go down here. What we've done now is we've included the weights. So you see this value right here, this bar right here used to be 1. Now it's 2 point something. You see it's even going above 2 because it had a weight of 2 point something. You notice how this bar right here used to be about 3. It looks like it's under 3. Now it's gone down just a little bit. This has gone up, this has gone down, this has gone down, this has gone down. The bars on the left-hand side have generally gone up. The bars on the right-hand side have gone down. And the result is when we calculate the declustered mean. Now look at this. This is not a big deal. We can calculate the declustered mean as simply the sum of the weights multiplied by the data values over all locations I through n samples. And all we have to do is divide by the sum of the weights. If we do that, we get the weighted average. Okay, what's really cool about that? If you calculate the declustered mean, what you'll actually get is a declustered mean of 10.07. Now that's awesome, because if you if you compare it to the clustered sample mean of 10.48 with 5% error, about 4.8% error, rounding up, and now you look at the true mean of 10.0, we now have an error rounded up to 1%, actually 0.7% error. We've dramatically decreased the error in our average by using cell-based declustering weights. So this is really epic. This is really cool. And so by using this methodology, we can greatly improve or mitigate the issue with error. Now, I want to give you an expert tip. And that is, I can't guarantee that every time you do declustering, that you will in fact improve the accuracy of this statistic. There's many pathological data configurations or cases for which it won't improve it. But in expectation, statistical expectation, in other words, on average, as you use declustering, you will move in the right direction. You will improve the accuracy. That's what I can guarantee for you. Now, there's a really important issue here, and a lot of people pick up on this as soon as I show this figure right here. You look at the cells and they say to themselves, but what if I change the size of the cell? How will that affect the data weights? And you're exactly right. It will affect the data weights. Let's do a mental experiment right now. What would be the weights if I was to make the cell size so big that all of the data are in the same cell? Just think about that. What would happen is all of the data would get a weight of 1, and you would estimate with the naive average. Your weighted average would just be the naive average. Now imagine the opposite end of the spectrum. Make the cells so small that every one of the data have their own cell. What would be the data weights? They'd all be 1 again, and you would estimate with the naive average again. And everything in between would change from the naive average. So what we do in practice is we run the declustering algorithm over a range of cell sizes, and we use a plot to pick the best cell size. So the standard declustering software will actually run over a range of cell sizes, going from very small to very large, and we'll calculate the declustered mean at each one of those cell sizes. Now, we know that if the cell size is very small, we're going to have a declustered mean equal to the naive mean. So that naive mean is right here. We could draw a line across right here. And as the cell size goes larger, we're going to approach that naive mean again. Now, we didn't go far enough. If we'd gone larger and larger, these dots would have kept rising up. Then what we do is we look at the shape of that curve and we pick the minimizing declustered mean in the case that we believe that we have preferentially sampled or clustered our samples in the high locations. Now don't worry about this. When you produce this plot, it'll be apparent. If you had preferentially sampled the low locations, this plot would be inverted. The values would come up and back down again. Why do we pick the cell size that minimizes the declustered mean? It's a conservative engineering choice. It's the most conservative choice we can make. Now, I'll tell you right now, there's no theory to say that that's absolutely the best choice. It's an engineering choice that we make. At the same time, we should recognize the fact that the results may be sensitive to large-scale trends. So if you do have knowledge by visual inspection of the data, knowledge about the way the data was sampled, about overall clustering scales, or you could employ some other type of sensitivity study, that would be very useful. I'm not going to get into those details. For the purpose of this class, let's stick with the idea of using the minimizing or maximizing cell size. Now, just to give you a little deeper knowledge about it though, can't help myself, you could choose the cell size so that in the sparsely sampled areas or parts of the area of interest, that you get about 1 datum per cell. And in the densely sampled areas, you would get more data per cell. That would actually be a good choice of cell size. But I don't want to get into all of those details and confuse people right now. That's a lot of tradecraft. Let's stick with minimizing and maximizing. Now, many students who see cell-based declustering get a little worried because of this issue of the exact location of the cell mesh. Look at this data value right here. All happy, 1 weight, just a king of the world, getting maximum weight, but it's right at the edge of the boundary. If this cell mesh was shifted up just a little bit, it would share its cell with other data and it would be demoted and get less weight. This is a problem. We don't want our result to be sensitive to the cell mesh origin, the location of the cell mesh. What are we going to do? We'll use a good statistical solution. We'll randomize an average. That'll remove the sensitivity. How do we randomize the cell mesh? Easy. We'll go ahead and we'll take random locations of the cell mesh, just 10 different locations of the cell mesh. We'll repeat the calculation and we'll take the average weight over those multiple weights calculated for each one of the data. So this data right here would have 10 different weights coming from the 10 different cell meshes. Calculate the average of that. Now you have a much more robust measure of declustering weight that's not sensitive to the location of the cell mesh. Let's just make a couple concluding comments about cell-based declustering. It's going to be sensitive to the choice of cell size. We're going to use the maximizing declustering mean methodology. You could also try to select based on data configuration. I gave a couple tips on that, but let me specify further. For this class, we're going to use the minimizing, maximizing. You're going to calculate the cell-based declustering mean over a wide range of cell sizes and take the minimizing or maximizing based on the shape of the plot. We're going to remove the sensitivity of the exact cell mesh location by averaging over multiple cell sizes. That's a parameter in the algorithm. It's going to ask how many. A big enough number is fine. 10, 20 is fine. It has low or little sensitivity to the data boundary. Now that's very, very interesting. Nowhere in this methodology does it ask what is the edge of the data? What is the edge of the area of interest? For that, we're going to use another form of declustering that is much more sensitive. It's quite sensitive to the boundary. That methodology is called polygonal declustering. And there should be no surprises if you were coming to this content from hydrology or other areas of spatial sciences where they do debiasing through weighting. This is the common methodology. Now, what do we do here? We're going to split up the area of interest. Here's our area of interest right here. The data points are shown as the black circles that are filled. We're going to split it up into Voronoi polygons or partitions. Not a big deal. All we have to do is take perpendicular bisectors between all of the data and intersect them up. Now, another way to think about this is we're actually segmenting the space such that if I picked a location anywhere in this polygon, the closest data, and I just mean Euclidean distance, the closest data is this data right here. Any location here, the closest data is that data there. That's why we call them polygons of influence. It's over what areas or volumes of the subsurface would I consider this the closest piece of information. Okay, now what we can do then is once we created our polygons, and this could be done in full 3D, not a problem, we can go ahead and calculate weights for each of the data just proportional to the area of the polygon. Where you have large area, you get greater weight. You're representative of more of the subset of the area of interest. So in this case, we go ahead and we calculate the weight at a location as the area divided by the sum of the areas, or in other words, the total area of the area of interest, or this can be done for volume, of course. Now, you can see immediately that for this methodology, the sum of all of the weights is going to be equal to 1. Just consider all of those areas, j equals 1 through n, and if you were to go ahead and put them through this equation and sum them up, you'd see immediately that's just equal to 1. Now, another convention, just like we talked about before, is to have the sum of the weights actually equal to the number of data. And for that, all you have to do is put n in front here. And the result is that the sum of the weights is equal to the number of data. And we're back to that situation that we discussed before where nominal weight is going to be equal to 1. Now, for this methodology up here, recall nominal weight would be equal to 1 divided by n, indicating data that are neither sampled in a manner locally that's too dense nor too sparse. Now, this methodology is very sensitive to the boundary. Imagine this case right here. You see how much weight this data right here is getting? What would happen if we were to expand the boundary out here? This polygon here would get bigger and bigger and bigger. Now imagine we made the area of interest come all the way out there. Now if we were in the classroom right now, I would tell you to imagine that we took the boundary all the way to Taco Joint, the taco restaurant I go to almost every day on campus there. Those were great days. Anyway, so in that case, we would have a massive all area for that polygon, and the weight to that data would be very large. Okay, so that's the polygonal based declustering. Let me just comment. People don't typically calculate the perpendicular bisectors and the intersections and to form these Voronoi partitions or polygons. It's computationally, it's a geometric operation that's a little expensive. What people often do is a numerical form of approximation through discretization. Super simple. What we do is we just form a nice fine mesh of locations. Many locations, like 1,000 by 1,000 or 100 by 100. And then you go ahead at every location, you find the nearest data, find the nearest data, find the nearest data. If you do that and you calculate the number of locations on that fine mesh that have this as the nearest data, I hope you can see that that would be an approximation for the area or proportion of area or volume for each one of these polygons. Okay, so a numerical discretization is often applied to solve that problem practically. Okay, declustered statistics. I told you already that we're going to calculate the data, and then we're going to also have weights for all of the data, and that's great. As soon as you've done that, you can calculate any sample statistic, and our sample statistic is going to be our predictive model here. And that sample statistic will be declustered. And you hope that it's reduced the bias. Okay, so for means, I already showed this already. You take all of the data, the sum of the weights times the data, divide by the sum of the weights. And if you do that, you will get the declustered mean. Sample variance, all we had to do was extend the equation for sample variance by including the weights multiplied by all of the square differences between the values minus their means. Here for generality, we show the sum of the weights minus 1. Now we're assuming the convention of the sum of the weights equal to n here, so not a big deal. This is equivalent to just n minus 1 here. And we can go on, we can carry on, we can calculate the covariance. Now in the case of the covariance here, We have the products. We've expanded the variance to talk about how two variables covary or vary together, I should say. And so we've expanded variance. Now we have the value, the sample, minus the mean for one feature, and for another feature, the paired sample minus its mean. The product of those, all we have to do is apply this weight. And once again, instead of n, we'll put the sum of the weights right there. We're assuming, once again, the concept of the sum of the weights equals to n. Now you can do weighting on the entire CDF. We already showed the histogram, not a big deal. If the sum of the weights is equal to 1, then we can go ahead and calculate the cumulative distribution function as just taking the sum of the weights for all data values less than a threshold. And if you do that, that'll give you the probability of being less than that value. Super, super cool. Really easy to do. And so we're able to go ahead and calculate CDF. So any statistic can be weighted. And so this is very powerful. And our statistics are a predictive model once again. Now, just in case you'd like a little bit of practice, I think I'll record a video on this later. But I do have on my GitHub account an example of declustering in Excel that actually is pretty cool. It takes a data set and it'll build a mesh, calculate the weights, and give you the naive distribution, the declustered distribution, the CDFs, and also the declustered averages and the naive averages. So you can make comparisons and you get to play around with the cell size and see how that impacts the result. Now, a much more rigorous approach would be to demonstrate to you how to do this using an algorithm that gives you the full outcome, the full result, the multiple declustered means over all of the range of cell sizes and so forth, the full workflow. In fact, I have the exact same workflow and data set that I showed in the course notes in a really nicely documented Jupyter notebook available on GitHub. So, great opportunity to get a little Python practice and to play around with an important spatial data analytics data preparation step of spatial declustering. Let me just make a couple of comments on cell-based declustering as we finish up here. I showed cell-based declustering in 2 dimensions. You can do the whole thing in 3D. But what I'd say is if the wells are vertical, it is a 2-dimensional problem. You really don't need to do full 3-dimensional declustering. You could calculate one weight and use the same weight along the entire vertical well. The sampling density is not changing vertically if the wells are vertical. Now, you could deal with full 3-dimensional declustering. Not a big deal. Now you have cells that are 3-dimensional. That's not so bad. We'll do that when we have horizontal wells, highly deviated wells. The problem is a 3-dimensional problem when it comes to clustering. The wells may be moving together in a way at different locations vertically, so the clustering is going to vary vertically. We've got to account for that. I should comment too, what we've shown has been isotropic 2-dimensional cells. Now in 3D, we'd want to use non-isotropic. In other words, the extent of the cells would vary vertically and horizontally. The choice of that cell size in each dimension is really related to the geometric configuration of the data, the sampling rate of the data. If you have a lot of data in the vertical direction at every half foot, as we often do, of course you're going to want to use a cell size ratio such that in the vertical direction you have much smaller extent than you do horizontally. You'll use the ratio of the data spacing. If the data tends to be 1 kilometer apart in the horizontal direction, but about 1 meter apart in the vertical direction, about 1,000 to 1 ratio. That's how we work that out. That was kind of more advanced details here, but we'll just focus kind of more of these simple 2-dimensional examples like shown in the code right here. Now, every time I teach a subject like this, I get students asking questions about unconventionals because unconventionals often have much more dense data sets. And they say, well, I get declustering in the deep water or other settings where we don't have a lot of data. It seems very sparse, but in dense spatial data sets or more dense spatial data sets, do we really need this? And so what I have right here is an example. I have the Haynesville, the Barnett, and the Fayetteville. And I worked this out. I took publicly available data and I looked at the initial production rates averaged over the first 3 months. And I went ahead and I calculated them over modern wells. I think they were recently drilled, long horizontal, multi-frac. I did a lot of filtering to make sure I was doing something pretty fair as far as pulling the data. I produced the distributions, and I looked at naive statistic, the average initial production, and I looked at the average declustered weighted initial production. And when I compared them, what I found was 4% overestimation using naive statistics versus declustered, 5%, 8%, and I had some other examples that were above 10%. So what do we find? Even in more densely sampled unconventional settings, we still have an issue with spatial sample. My advice to you as you go out as a professional geoscientist or engineer, assume all spatial data sets are sampled in a biased manner and address this. All right, I hope this was helpful to you. That's the end of my discussion around declustering. I will next get into the topic of debiasing, where we use secondary information to assist us in correcting for bias. Remember, in the case in which we have failed to sample part of the distribution, we can't use declustering weights. We need a different technology. And I'll get into this next. All right, I hope this was helpful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and work and conduct research on geostatistics, data analytics, spatial data analytics, and spatial machine learning. I hope this was helpful to you. Everyone, take care.